No, because lambda will do that. It would need a decorator if I wrote a function, but the lambda is it's one of those automatic deterministics. Just like normal doesn't need a stochastic decorator. Okay, so it doesn't get much more succinct than that, right? It's one line for anything you would write on the whiteboard. Okay, pushing on here, that's how you write a model, and we'll use it later. How do you fit them now that you've written them? And all we've seen so far is MCMC. There are actually a couple of others. One called MAP, which stands for maximum a posteriori estimate, and the other is norm-approx, which does a normal approximation to the posterior. And so the MAP actually uses SciPy's optimized package. So it essentially assumes that the posteriors are all going to be multivariate normal. And in fact, in the limit, if you get more and more data, they will be. You can show analytically that the posteriors will be multivariate normal, but not in general. And so it'll give you an approximation. So what you do is instead of passing your model to MCMC, you pass it to MAP, and you call fit. And you'll find that will work quite quickly. And then the values of each of the parameters will be the posteriors. And essentially gives you back the posterior node, the estimate of the posterior mode. Nothing else. What I find this is good for, actually, is picking initial values for each of the parameters. So it'll often give you a lousy approximation, but it'll give you a good starting point for doing MCMC. So there's nothing wrong with taking that model now, wrapping it in MCMC, and running MCMC on it. It does give you other goodies like AIC and BIC, which are model selection criteria, for those of you who are into that kind of thing. And I've just listed the attributes and methods. So the fit, you can specify which SciPy optimizer to use. It uses fmin by default, but you can give it something better, BFGS or what have you. Powell works usually the best, I think. Yeah. Normal approximation is it's similar, but what you get here, if you fit that model, you get posteriors of that normal. And so in this case, this is the two-parameter model. I get a posterior mean and a variance-covariance matrix. This is the posterior variance-covariance matrix. So a little bit more information here. And what you can do, because you have the variance-covariance matrix, is you can sample from a normal approximation. So you can sample from that multivariate normal. And so I do that here for alpha, and that's my posterior sample for alpha, if you're happy with that normal approximation, which much of the time we're not. Okay, we're more interested in MCMC, I think. MCMC, the important methods are sample and iSample. So sample takes how many iterations? That's the only required argument. Also takes burn-in, thinning, if you want to do that. The tuning interval, so how often it checks to tune. By default, I think it's 100, but you can set it to 1,000 or 10 or whatever you want. Tune throughout, which is just a flag. Do you want to tune all the way through, or do you want to stop when burn-in stops? Save interval, it will save the model every several iterations if you're worried about your model crashing on you. iSample is the same, but it does this interactive thing that's quite nice. Here, let me just do a... just going from pymc import MCMC. All right, so if I do MCMC Gelman bioassay, okay, there's my Gelman bioassay model, and I do iSample. Let's do 100,000 iterations. I get this. So I can see what iteration it's at. And I can pause it. I can put it to the background if I want to. I can also set a verbosity on this too. And what that'll do gives me updates on its acceptance rate, how it's adapting to things, what its value is every 1,000 iterations or so. So if you like that, kind of slows it down, writing all that stuff to the screen, but some people like that feedback, particularly for slow models, long, slow models. We saw before a use step method for overriding the default choice of step method, stats and summary for output, and yeah, and then trace. We get all the traces. Those are the important ones. The step methods, I've shown you the important ones here. So Metropolis, and when you when you want to re-specify the step method, you can also pass an arbitrary number of arguments to be passed over to Metropolis. So if I want to give it a proposal standard distribution to start off with, I can declare it to be normal instead of something else. It'll be passed on. So here we're giving it the new step method, the parameter to which it's going to be applied, and then its other optional parameters. These step methods, one of the reasons I think pymc works pretty well is that everything is highly compartmentalized and independent. So the MCMC object knows nothing about updating an MCMC algorithm. The step method only knows how to take one step of the given MCMC. It doesn't know how to burn in and thin things, and it doesn't know about storing traces. Everything is independent, so you can swap all of the elements out. If you want to pop another step method in there, if you want to pop another back end in there, it's very easy to extend it in that fashion. Similarly, MCMC is a subclass of sampler. Well, there's other sampling methods that you can use for doing Bayesian inference. You can do approximate Bayesian computing. You can do sampling importance resampling. All of these, they're all iterative simulation-based methods that aren't MCMC. And so we haven't done it yet, but you can do, actually somebody has done importance sampling. There are some third-party extensions to pymc that do things like that, and you can. So Metropolis takes arguments like the stochastic, the proposal standard deviation, the scale. The scale is the parameter that gets tuned. So you pass it a proposal standard deviation. It doesn't actually change that directly. It changes a scale factor that gets multiplied by it, so it keeps that original value in place. Proposal distribution. Currently, it only supports normal and prior. You could implement one that uses a t-distribution as proposals as well, but I'm not sure it's really worth it. Adaptive Metropolis is what I was telling you about before. This is not just the tuning Metropolis. This one is adaptive in that sense already. Adaptive Metropolis is an algorithm by Hario et al. That can make things more efficient because, again, it block updates a whole set of parameters simultaneously using a multivariate normal proposal instead of univariate ones. So if you've got, particularly in hierarchical models, for example, when you've got a whole array of the same variable coming from a similar model, you can use adaptive Metropolis. It's also very good at models that are parameters that are highly correlated to one another. And what you can sometimes get in highly correlated parameters is they'll chase each other around their parameter spaces. And block updating them can help stabilize that sometimes. And I told you before, there's discrete Metropolis, binary Metropolis. These are just subclasses of Metropolis. And so, again, it's very easy to subclass any of these things to make it do what you want it to do if it doesn't do it already. Seen this already. That's it for that. Any questions about? Yeah.
Is there anything built into the MCMC class to estimate the value of the denominator?
No, but you could. It's easy to do, right? Because no. The answer is, to your question is no, but it could easily be done because it's just the posterior divided by the it's the likelihood in prior divided by the posterior. So you could calculate it. Yeah, the denominator is sometimes called the prior predictive distribution. So it's the distribution of the data before you've seen, because you've conditioned out all, or you've integrated out all of the values of theta. Yeah.
Can you have a deterministic node with observed equals true and have parents of that are stochastic?
There is no observed flag for deterministics because it's deterministic is some function of the values, and when the values that are passed to it change, it will change. So there's no mechanism for doing that. What would you? You could use a factor potential to enforce that. You're talking about you always want this deterministic to sum to this particular value or something like that.
And that's what I've actually observed.
Oh, okay. Then I would use a factor potential then, because deterministics don't really affect. They're just an arbitrary transformation of other stochastics and other deterministics. If you want it to influence the model, you're essentially applying a constraint. You're applying a sum to constraint or something like that. Then that's what a factor potential is for. Yeah, you could. It's hard. We've found it hard to do reversible jump generally. In fact, you'll find the skeleton in the sand. There's a sandbox in pymc2 that contains some stubs of reversible jump attempts. So a reversible jump is a really cool thing where sort of takes MCMC to the next level, in that it not only uses, not only thinks of the model parameters as being unknown, but the model space itself as being unknown. So it's a way of doing model selection. And so every time it proposes, it not only proposes values of parameters, it proposes models. Okay, so it will search over the model space. So if you've got 1,000 parameters and you don't know which ones belong in the model, you can use reversible jump to say, all right, I'm going to include this subset in this iteration, and in the next iteration I'm going to use that subset. And you can use that to estimate model probabilities, posterior model probabilities, which is really nice. You can get a distribution of the probabilities of all the models. There's a really good paper by Ruth King and Stephen Brooks where they do that for a survival model of shags, which are cormorants, I guess. And they evaluate something on the order of 400,000 models in one reversible jump implementation. It's a little scary, but that's the nice thing about Bayes. You don't know what it is. You know what the real model is. Well, let's make the real model a variable in our model. But the tricky thing about it is that it involves this bijective term where if you're changing the size of the model, you have to account for the change in size of the model. Otherwise, detailed balance doesn't apply, and so it's hard, and those involve derivatives. So now pymc3 uses Theano that does automatic differentiation. So we may be able, it might be easier to do in pymc3. So we'll see. All right, I'm not doing too bad here time-wise. So let's cover model checking. And if I have time, I'll just show you a quick example of a bigger model. So model checking, there's a number of aspects to model checking. One is, did the mechanics of my MCMC algorithm actually work? Irrespective of how good or bad my model is, did MCMC work? In particular, did the model converge? Have we converged or not? Then there's the issue of, is this the best model I could have made? What about other models? There's relative stuff. And then there's goodness of fit, right? In an absolute sense, is this model an adequate representation of the data? And you really have to do all of them. You don't have to do model comparison, I guess, but you at least have to do convergence diagnostics and some form of goodness of fit. And I'll cover these kind of briefly because they're not terribly interesting. You just got to know that they're there. So we're promised by the theoreticians that MCMC will converge as n goes to infinity, And so, but how close to infinity do you have to get, right? We have theses to complete. What we want to know, we'd like to know the minimum number of samples that we need in order to get, some good posterior inference. And how do we know that we're there? There's there's no universal rule of thumb even for that. It's not, well, your model has 8 parameters, so you should probably sample 10,000 iterations. It depends on your model that you specified. It depends on your data. It depends on which samplers you choose. It depends on the initial values that you chose. It depends on whether you're, all of these things. And so it's led to the development of a bunch of criteria for establishing convergence or not. And there's a set. First, they tried to do things analytically, right, where sort of establishing theoretical bounds on the variance and things like that. It's very hard to do and difficult to use, and so they that was sort of abandoned early on. More commonly, folks use statistical approaches, and by statistical I mean it uses the trace, the values that you sampled, to try to see if that comes from a converged model or not. And so the problem is that all of these diagnostics are heuristic. You can't prove convergence based on the output of a statistical convergence diagnostic. Right? You can show lack of convergence, but you can't establish. It's kind of like falsifying a hypothesis versus proving a hypothesis. You can do the former, but not the latter. So what the best thing to do is usually to run several of these things, and if they all come out clean, you cross your fingers and submit your paper. Okay? And so for some things, you don't even know. There are informal methods that you can do. The first thing you always do are informal methods. And these are the obvious ones, right? So here, let me clear all this stuff. So you run a model, and it sucks. And you know that this model has not converged, and I haven't run any diagnostics, right? How did I know that? Right? You just know this hasn't converged. And so that's evidence for lack of convergence. You go back. What did I do wrong here? I sabotaged myself. I set the tune interval to 1,000 and only sampled 1,000, right? I deliberately made this not work. So I would run this longer. I would tune it better. I would use a different step method. So this sort of inspection of traces is one way of looking at it. So this one looks pretty good, right? Look, it's relatively homogeneous. It's stationary. It's not going up. It's not trending one way. The variance is pretty consistent, right? It's not getting narrower or wider. That's good. Those are all good things. And in fact, some of the more formal methods just kind of put a number on that, on what you're looking at with your eyeballs. So maybe not terribly useful. One thing you can do is, run the chain, chop it up into pieces, and look at the histograms of those. And say, well, look, you can't tell which came earlier than the other. That looks pretty good.
Is the stationarity guarantee convergence?
Nope. No. It's a byproduct. It's a property of convergence.
So all those plots would look exactly the same.
Mm-hmm. Yeah. So I'll talk about this a bit more, but what you can sometimes get, and it doesn't happen in these small models that I'm running here, but in really big models, you can get what's called metastability, where it just rocks along like that for a long period of time, and you're happy. And then if you let it run another 1,000 iterations, it goes boop and pops up here. And that's because it's particularly if you can get in situations with crazy models where if you've got if this is in 2 dimensions here, and you've got like a bimodal thing going on, right? And so you could get your model hopping around in here for 1 million iterations, and then all of a sudden it found its way over here, right? How would you know? You don't know that your posterior is bimodal, right? Until it gets there. And so you can never tell for sure. That's what I talk about. You can never prove that you've converged. You can only be confident. Another nice thing to do is, and I highly recommend this, is run more than one chain at disparate starting values. So I've taken this same disaster model, started the early mean at 0.5 here and 5 there, and you run it for 1,000 iterations. This inspires confidence, right? You started at different places in the parameter space, and that's ergodicity. And we like that. But you got to do that for all the parameters. So it's one really good way of helping diagnose things is running multiple chains, because this is a stochastic thing. There are a couple formal methods. Three of them are implemented in pymc. One is the Goveki diagnostic, and what this does essentially is it compares later chunks of the chain to early chunks of the chain, and it transforms them into Z or Z scores, and so as you're standardizing, you're making them into standard normal distributions, and then you simply look at those Z scores, the differences over as the chain progresses. And what you'd want, if things are running well, is for all of those Z-scores to be between 2 standard deviations, approximately from 0. And so it's easier just to show you. Okay, and so in this case, so it's comparing the last 50% chunk of the chain to little snippets along the way. And you can see that we've got quite a few that are popped out there. So we wouldn't be happy with that. You'd want them all to kind of be in this little shape. So you'd want to run that one longer. So you give it, the arguments are, the first chunk. So here it defaults to the first 10% of the chain. Last defaults to the last 50%. And it just keeps moving that chunk forward. Second diagnostic, Raftery-Lewis, don't use it very much. It's more of a planning tool. It attempts to tell you how many samples you need before convergence, and I just don't believe that it works. It's basically, it uses how well it can estimate a particular quantile in the posterior distribution, and as that estimate gets better and better, it's happier with convergence. And it just gives you these really precise estimates that you don't believe, right? So you run it here. So I'm going to try to estimate the 2.5 quantile within 0.01, and the default is 95% accuracy. And so I run Raftery-Lewis, and it tells me I need 937 iterations with a thinning factor of 1 and discard 11 iterations. Nope. It's just a number. Yeah, take that and multiply it by 3. It's so cheap to get samples. Like, why would I would never, I would run this model if I was to publish something, I'd run it for 100,000 iterations or overnight and run it for 1,000,000 iterations. Who cares? It's just CPU time. So I don't worry about planning things that well, but you can do it. One that's really good, though, is the third one, the Gelman-Rubin statistic. This is essentially an analysis of variance of your traces. You remember analysis of variance from statistics class, right? You used it to determine differences between groups and stuff. And here what we do is we take multiple chains, and what it does is it estimates the between chain variance and the within chain variance. And it turns out that you can estimate the variance of theta as a mixture, a discrete, finite mixture of the within chain variance and the between chain variance. And you can see from here, n is the number of iterations. As n gets large, this thing will go away, right? This, not really, right? It converges to w, in fact. And so early on, this ends up underestimating the posterior variance. This ends up overestimating it. And over time, they should converge. And so our hat is just a factor. It's just the ratio of this whole expression divided by w. And it should approach 1 as sampling goes on. So what you want are values of our hat around 1. So so you need multiple chains, and pymc2 doesn't do parallel chains. pymc3 does, but you just run them in serial here. And so the Gelman-Rubin of that is it gives you these are our hats for each of the parameters. So it's 1, 0.99, 0.99, 1, 0.99, 0.99. We don't really care about theta because it's a deterministic anyway. These are the only ones that are important. And in fact, when you run summary plot, remember I showed you the forest plot before? If you have multiple chains, it will calculate R hat for you automatically. And it'll plot it over here. So what you look for is that. That's good. I'll show you an example where it doesn't work out so well. Okay, that's convergence diagnostics, right? Those are 3. So, run a couple of those, see if you're happy. What I'm going to talk about now is just as important, and that is checking your model in an absolute, you can run a model and have it converge and everything, but your model can still stink, right? It can still just be a bad model. There's nothing preventing a bad model from converging in the sense that it just doesn't fit very well. And one of the ways that we can evaluate things, because we're already sampling, we're already able, you saw how easy it was to impute missing data. What we can do is sample from our model. We can sample data from our model, because that's what we're doing for missing data, right? What we do is we sample new data from our model, conditional on our model, and we compare that distribution of simulated data to the data that we already observed. And we see how compatible they are with one another. Right? And so if your simulated data is over here, and your observed value is over there, we're not happy. But if it's here, we could say that our observed value could plausibly have come from that model. Right? That's kind of the idea behind it. Andrew Gelman calls it posterior predictive checks, and pymc can do some of that stuff. So here I gave away the model. Here's the model that we were fitting before. This is the bioassay model, and so it's really easy to do. All we have to do is add one more line to our model. And that line will look exactly like your likelihood, except observed will not be true. And you can give it a value, but the value won't stick around for very long, because this is going to be an unknown. This is now an unknown variable in your model. And what's this going to do? It's just going to sample data sets for you. The value is just going to get sampled at every iteration. Okay? And so I can run this model. And there's a function, plotting function called GOFplot, and it does exactly that. It takes the distribution. So for every data point, so this can be a little storage expensive for a large model with lots of data. For every data point, you get a distribution of data. So it's simulating that data point. And for every one of those, it puts a little red dotted line under the true value. So here you can't see it because matplotlib. And here it's here under 1, and it's 3 here, and it's 5 here. So those red dotted lines could plausibly have come from that model. You could easily argue. And so that's a pretty good goodness of fit check. Another way is to calculate Bayesian p-values, which are nothing like regular ones, so don't be scared. What it does, you essentially calculate a statistic, in this case called a Freeman-Tukey statistic, that measures distances between expected values of data and data, sort of indirectly doing what the posterior predictive check is doing. And pymc has this built in. And so what we're doing is we're checking the probability that the simulated discrepancy is larger than the observed one. And you'd hope that they would correspond pretty. They'd kind of fall on a diagonal, right? The only reason they should be different is just due to random noise. And so we can import discrepancy from a model here, and we can calculate Bayesian p-values for an entire model. And so, and again, you want values that you don't want 0.99999, and you don't want 0.00001 either. You can plot these discrepancy points as well, and you should get something sort of like this. So what you don't want is, all of these values in this quadrant. It may make funny shapes like this, and it's just an artifact of the model sometimes, but that's pretty good. And that gave you one more exercise that we don't have time to do, but I recommend you work through it. This would be a good, I would go away if you have time, tonight or some hotel room or something, so you'll forget this stuff if you don't apply it right away. Implement this mod. This is a meta-analysis of the effectiveness of beta blockers. So there's control and treatment, and you're building a binomial model for each of those where the control is just a population mean, and then the treatment is the mean plus some effect of the beta blockers. And then and that delta has a normal distribution. It could be positive or negative. You don't know a priori. And so the idea would be to take the data is given for you here, specify this model and see if that model fits. If it doesn't fit, you can do some you can change the model structure slightly to try to make it fit. 10 minutes to 5. I've never managed a tutorial this tightly before. So what I want questions about model checking. Don't want to underemphasize the importance of model checking, even though it can be a little unsatisfying sometimes because it's all based on kind of heuristics and simulation.
So what you described where you sort of like the values to check, is it sort of this cross-validation, right?
No, cross-validation would be more like if you were checking the sensitivity to, I don't know, different values of parameters. Posterior predictive is the idea behind that is that there are two components that make prediction hard. One is our lack of knowledge about the system, so sort of epistemic uncertainty, and then the other is sampling very aleatory stuff that collecting more data doesn't help. It's just this is a stochastic process that even if you knew what the probability of somebody dying of lung cancer is, well, it's still a flip of a coin. It's just the probability of tails is different, and that never goes away. And so the posterior predictive distribution includes both that parametric uncertainty and then also sampling variability. Whereas the posterior, if I collect more data, all those posteriors that you would see, well, I don't have any in this one, all these posteriors here would just be single point masses on the posterior value. You can shrink those literally to nothing by collecting more data, but you can't get rid of binomial sampling variability. It's just part of the system. So the posterior predictive combines both, the sampling piece and the uncertainty piece.
Can you comment on the differences between pymc 2 and 3 and what you would recommend as transitioning 3?
Yeah, so pymc, so there's new developers. So I'm not a good programmer, and so the reason pymc has come as far as it has is I've always been able to convince better programmers than me to come onto the project and contribute to it. And so Anand Patil and David Heward, who I've still never met in person, did a lot of the pymc 2 stuff. Pymc 1 was my crappy postdoc project. Pymc 2 is this nice thing that I'm presenting to you here, and that's largely their work. And then they got jobs and went away, and so now there's a new set of developers, and one of which is John Salvatore, who works for Amazon, and he's really good. And he got very excited about Hamiltonian Monte Carlo, which didn't even get into. So there's a bevy of new, way more efficient MCMC algorithms out now, and the pymc 3 is trying to implement those. And part of the difficulty is that it requires things like automatic differentiation and those sorts of things. And so what we've done with pymc 3 is we've gotten rid of all of the Fortran stuff, and we've made Theano its back end. And Theano is a way of doing can do symbolic differentiation and various other things will allow us to do GPU calculations too. So the long-term future looks very good. The problem is it's kind of hard to debug sometimes. It's a different set of problems. But I use pymc 3 and 2 interchangeably in my own work, depending on what I need. It's a little bit more manual right now in terms of it doesn't have all this nice automatic imputation of missing data. It doesn't pick MCMC samplers for you, but it does a lot more. And so I had hoped to be doing this in pymc 3 when I proposed the tutorial back in January or whatever. It's just the three of us, our three main developers, we all are paid to do other things. And so we haven't been able to push it forward as much as we like. And so this is also a recruiting call. If any of you are good at this stuff and want to contribute, let us know, because there's a lot of stuff to be done. So what we've done is we tried to keep the syntax as close as possible. It's very, very similar syntax, extremely similar. In fact, to the untrained eye, they look exactly the same. And it even has some niceties, like it uses Thomas Wiecki implemented Patsy equations. So if you're just doing a regression, all you have to do is go y tilde x, pass that to the GLM module in pymc3, and you can do a regression in one line using MCMC. So it's really sweet. So it's going to be really good. It's just, I figured for an intro class, it's better to use this because this is rock solid. A lot of the stuff is automated. And learning this won't hurt you from learning pymc3. So that's the answer there.
Are there any examples of where the likelihood function is not analytic?
As in, you can't write it. What do you mean by not analytic?
You can't write it down.
Well, if you can't code it, you can't implement it. So you mean closed form, like just non-parametric, maybe, or?
Because the system different. Suppose that for, okay, so the use case that I have in mind, for a particular set of parameters, so suppose I define the likelihood, or I derive the likelihood function. I observe some data, and I make my model for a given set of parameters will predict something that I can look at the data, or I can compare the data, and that would be like the residual, and I can maybe assume that the residual is normally distributed, error is normally distributed. But my model predictions for a given set of parameters require numerically solving a differential equation. It does not have that.
As long as you can write a function that returns a log probability, yes, whatever's inside there can be whatever you want it to be. So yes, you could.
That's right. So
you just have to.
I can write a Python function that will numerically solve different equations.
It'll be slow as hell, but you can do it. If you're having to do that every iteration. Yeah. Let me just, before I answer any more, let me just do one, what do you call it, motivating example. It's not motivating anymore, we're done, but just kind of a real world example. I've got manatees or autism. All right. There's just two examples of using pymc to do kind of bigger, more realistic models. So manatees, everybody knows what manatees are, right? They're large marine mammals. In my former life, I was a marine mammal biologist and still do some of this stuff. And so manatees are endangered species, or they are for the moment. Might not be next year. And what we're often trying to do is assess the population. Are there enough? Do we have enough manatees? We don't know. And that's what they want to know is, if they're trying to set thresholds for population size, for reclassification, or if something goes wrong, they want to be able to monitor it. And so, but the problem is, manatees are hard to count, right? They're underwater a lot of the time, and they move around a lot, and so on. And so what we do is we have aerial surveys that we go out and count manatees. But the problem with counting manatees is, of course, you're going to miss some of them. And so your count's always going to be biased low. Also, you can't sample your entire study area comprehensively all the time. And even if they're there sometimes, they might be underwater. So there's a lot of uncertainty. So you want to estimate population size. And so we go out on helicopters. And so this is an area in South Georgia near Brunswick. This is a Navy base that we're not allowed to fly around. And these are some sampling plots. And we essentially just circle around with our helicopter, and there are two independent observers. And so they're both looking at the water at the same time, independently recording manatees that they see. And the reason that there are two independent observers is that there's two confounding processes at play. One is, if you don't see a manatee, it could be because it's not there. It could be because it's there and you missed it for whatever reason. Where if you have two observers, you can actually separate that information a little bit. Because if it's not there, neither observer is going to see it, although I guess you can have false positives. They can look like logs quite a lot. But if there is one there, with some probability, one person might see it and the other might miss it. And so you can separately estimate these quantities a little bit. And so what we wanted to do here is estimate the number of manatees in South Georgia during the summer. And the other fold, the other fold of complexity here is that it's a migratory species. So all these manatees, they don't live in Georgia, they live in Florida. They migrate up the coast when it gets warm and back down again. And so there's monthly variation in the number of manatees that you see. There's annual variation. Some years, more will come versus others, and so on. So what we did was we built a hierarchical model. This is one of these more complex models that we were talking about to try to estimate those. So lots of data processing. This is nice to have these IPython notebooks because you can reproduce what you've done here. I'm just going to skip down to the model. Here it is. Okay. So we're going to have a couple of different models. We're going to have a sighting model, probability of seeing a manatee given it's there, and then there's an occupancy model. What's the probability that this plot has one or more manatees on it? And so our sighting model has a number of covariates. One of those covariates is water clarity. So in addition to counting manatees, we're actually taking an index of the clarity of the water. So if it's murky, and the manatee's underwater, you're not going to be able to see it. Sometimes it's crystal clear, and manatees are, bigger than 4 of us, and so you can see it even when it's underwater. So this is where we're making this probability of sighting more complex by incorporating this clarity covariate. And then we got a mean for observer 1 and observer 2, and then realized detections for the first and second observers. So we're going to be modeling these as a mixture distribution. So we're going to get a lot of more zeros than you would expect from a Poisson count because of occupancy. And so we're going to build a slightly more complicated model for these counts. And we're going to, every time that we go and take a sample, it's going to be influenced by our probability of detection. And then there's this occupancy model down here. And this occupancy model is going to vary according to month and year primarily in this case. And so we're going to build a little linear model here. Oh, and there's also a random effect for plot. So you saw that map of all of the plots. Well, there's going to be variation to the degree to which each of those plots is occupied by manatees. Maybe some of them have more seagrass than others. Maybe some are warmer than others. We just didn't go out and measure that, but we do want to account for this variability and not treat them all as the same. So we've got a random effect for plots, and then we have fixed effects for year and month. And so this is going to, so we've got a little submodel here for occupancy, and here's our deterministic here. And it's an inverse logit where we factor in the plot, the year, and the month. So one linear model there, another linear model up here, and then we combine both of these down at the bottom to model abundance. Okay? So this is going to account for the number of manatees we might have missed due to us not being able to see them, and as a function of occupancy. And so down here we have pymc includes what's called a truncated Poisson, which is Poisson that's either truncated below or above. In this case, we're going to truncate it at 1, and then we're going to count for the zeros by the occupancy probability. So it's a mixture model. It's going to be 0 with probability p, and that's inverse of occupancy. And if it's occupied, it's going to have a Poisson distributed, truncated Poisson distributed count. So it's what's called a zero-inflated mixture model, more zeros than we would expect. All right, and so, so we've got, so our observation model then includes this estimate of n, which is unknown, n is what we're after, and our estimate of the probability of detection. So we pop both of those in for observer 1 and observer 2, and these are our likelihoods. They're binomial likelihoods. Right? So if I have a 90% probability of seeing a manatee that's there, then we can model that with a binomial distribution. And then, because we're good analysts and we do model checking all the time, we include a predictive one as well. And so, some convergence issues. Here's where our hat doesn't necessarily work all the time, so you'd want to sample more in this case. but cutting to the chase here, we now get posterior estimates of every, this is the total, this is the sum of all of the plots over 3 years. So 2009, you can see what happens here. So this is April, this is July, August, and so on. So the manatees come, they go away, they come, and they go away. And the red dots are the observed number of manatees. These are the estimates, the red lines, the posterior median intervals, and so on. And so you can see we've got estimates of what the number of manatees we missed, which is what we want. So we can use these estimates as sort of planning tools. You can see in some years where the manatees go in there that year. And then for each of these, we can go down and do our checks. Oh, I thought I had checks here. I did them in another notebook. You have to trust me on that. That model fits pretty well. So that's the idea, is multiple covariates affecting your model at different levels. You could have individual observer covariates. How experienced is your observer? You could have more information about those plots. What's the proportion of them with seagrass in them, and so on. So you can make this as complicated as you have data for. No, it isn't. We're trying to publish this, so a paper will come out soon. 5 after 5. I think we probably need to stop there. But if any of you have any questions, feel free to come up to me either after this or I'll be here the rest of the week. So thanks, everyone.